Today we are just going to review, so we may turn out a little bit or get done a little bit quick just because there's not that much calculus to review. What have we done so far? Well, we had one assignment that was making sure that you knew how to do your calculus. Those are graded and returned to you guys. Hopefully you've looked at them just to see how they were graded. Almost in every case, the people knew how to do the integrals. Where they lost points was for not following the showing explicitly how it's done. But the scores were relatively good there. And then we did the kinematic equations. So what would we have on the test? We're going to have, for our calculus problem, the one calculus problem is going to be something that uses one or both of those relations. So being explicit, there are 5 options here that we could do. We could have the acceleration as a function of time and find the speed and or position as a function of time. We could have the position as a function of time and find the speed and or acceleration as a function of time. Or we could have the speed as a function of time and find either the position or acceleration. Or, and now the last two are where it gets a little more complicated, we could have the acceleration as a function of the velocity and then have to solve that for acceleration, velocity, and position as a function of time. And the last one I put there is have the speed as a function of position and then find speed, acceleration, and position as a function of time. So your problem is going to be one of these variations. Now, Nathan was, I've got to remember how to do integration by parts. What if I forget that on the test? The integral or derivative is not going to be something that is complicated. It would be likely either exponential or a polynomial / power relationship. So I'm not, this isn't a calculus class per se. I'm not going to check to make sure you know all of the details of all of the different calculus things here. Now that we've gone through the basics for calculus, I'm assuming you know how to do those things. If I'm going to give you something that requires harder integration, I will be, or taking a derivative, I'll give you, equation sheets for the calculus forms as well. I don't want that to be an impediment as long as you know how to do calculus. So let's just head in with these examples. So which one would you like to see first? Nathan chose 1. So number 1 it is. So suppose we have acceleration Is that what it was? Okay, we have acceleration like this. First, I'm going to ask you just a question about thinking. With this relationship, what's happening to the acceleration in time? At time equals 0, what would your acceleration be? Not 0. 1. It'd be 1 at time equals 0. And then what's going to happen to the first term as time moves forward? The e to the minus bt. It's going to go down. What's going to happen to the second term? Go up. So after a long time, it's probably just going to look like ct is your acceleration because the first term is going to disappear over time. So we can look at that and get an idea of what it means, but now let's just do the work, because if it's on the test, you want to be able to show what the work is. So what's the first thing you do? Step number 1. Oh, we're finding the position as a function of time. It was find speed or position, so I'm going to do the position one. Okay. So what would the step 1 be? That's actually going to be step 2. It's one of the steps, though. I'll put that right now. What's our first step?
Define acceleration.
Okay, she said define acceleration. We are going to substitute A is dv dt, which I believe is what she meant by define acceleration. How do I know that's my first step? I know it's my first step because I want to move to velocity and then to position. And I know acceleration relates velocity and time, so that's going to be an equation that allows me to remove acceleration and get it into the velocity, which is a step closer to position. And of course, it gives me a calculus equation because you know that I have to use calculus on this. Okay, what's step 3? After we've separated the variables, what are we going to do then? Integrate both sides. Independently. Independently because one side's only going to be a function of v, and the other one's only going to be a function of t. So now it's time to do the work. So step 1, dv dt is equal to e to the minus bt plus ct. There was no question to ask you because it was just substitute for a. Now step 2, I have to decide how to separate the variables. So I need to identify what are the variables in this equation. So if I look at the equation I wrote for step 1, what are variables and what are constants? So first name the constants. Let's get those out. Okay, B and C, I'm negative. B and C are constants. What are the variables? T and V. Well, nobody said D. What's D? It's a calculus symbol that says we're doing a derivative. What it means is infinitesimal amount of whatever follows. So dv means infinitesimal amount of v. Or infinitesimal change, I should say. So I need to separate the variables, so I need to have all the v's on one side, all of the t's on the other. And I need to make sure I have my d's all on top. So that means my dv should stay where it is. How am I going to get the dt not where it is? Multiply across. So I'll have dv is equal to and there it's completely separated. Only v's on the left side, only t's on the right side, plus constants that we don't care where they are. So step 3, integrate both sides independently. Now, I do expect everyone in here can do these integrals. So integral of dv is just v. Have to remember that it has limits. Integral of e to the minus bt is going to be e to the minus bt divided by the derivative of the exponent. The exponent derivative is minus b. And then integral of ct squared over 2. Remember in that first homework assignment, I made you show like ct to the 1 plus 1 divided by 1 plus 1 to make sure you know how those steps work. Now I see, okay, they know how it works. It's ridiculous to show that. Now I have to put in the limits. I brought the minus that was in the denominator out in front. Let me be a little more explicit here. So there I was very explicit. I have the upper limit minus bracket the lower limit. And in the lower limit, one of these terms, this one here, goes to 0. What does the numerator go to in the first one? E to the minus 0? 1. So I'm left with moving the V initial over, so V final minus V initial became V final equals V initial. And so there I have my equation for V final. So if I was asked to find the speed as a function of time, I would be done. But I want to find position as a function of time, so I have more to do. So I have to take this and continue. First step in continuing is to relax. V final was the speed at whatever time I stop. T final was whatever time I stop. So I'm just now going to let V final be called V again and T final be called T again. I had to put V final in my integrals because I can't integrate and have my limit the same as my variable of integration. So to be a legal mathematician, I had to have something besides just V and T. But now I'm coming back to that. And we're trying to get to position, so I'm going to replace V with dx dt. So it's kind of like sing-song second verse. I have the equation then that says dx dt is equal to So I've rewritten the equation. Did I miss something? No. Nope, I didn't. Just seems that way. What do I do now? Separate variables and integrate again. Changing the order. So now I have those separated. I'm going to integrate. And so I'll have that beast. And the final step will be putting in the limits. Notice I put in the limits on the left side instantly. It, once again, doesn't really bear writing to write x limits from x initial to x final. So if I solve this for x final, move the x initial over, And I'm out of space. Perfect. Okay, I'll hide that and continue writing. Minus so I'm only going to have to put a minus 1 over b squared with it. So in the end, I have my x final is equal to x initial plus v initial t final plus t final over b plus e to the minus b t final over b squared plus c t final cubed over 6 minus 1 over b squared. Getting to the answer, of course, is good. Being able to do the steps is what I care about. Now on the test, you're only going to be tested on the final answer. So if I were to give you something like this, I would give you numbers to plug in and you would have a number for your answer for this is the distance it's going to travel.
So going to the green line.
Yes.
When you integrated the e to the minus bt.
Yes.
So you pulled down. Well,
Yeah, I did it quick.
You like the when you integrated it was the. See, it would have been the from what you're integrating to.
Yeah.
It would have been that stuff times minus b.
Divided by minus b. Because when you're integrating, you divide by the derivative of the exponent. When you're taking a derivative, then you bring down the derivative of the exponent.
Okay, so when you're doing the derivative of ct squared over 2,
Yes.
when you integrate it actually.
Well, I did the right.
Yeah, so it becomes a 6 upon because you multiply.
2 times 3 is 6.
Okay.
Because I took the 1/2 and then divided that by 3 gives me 1/6. Do you have a question, Trish? How about you, Kaylee?
I'm a little lost on the 1 over b squared in the bottom row.
This here?
Yes.
Okay, so this line here was putting in t final. And then I have minus, and then the thing in the bracket is putting in 0 for t. And so this term here was 0 because it had a t. This term here was 0 because it had a t. This term here was e to the 0 over b squared. And so e to the 0 is 1, so that was 1 over b squared.
Okay.
And then this one was 0 because it had t.
Okay.
Okay, Nathan chose 1. We got 4 more options. What else can we do here? Choose one.
Let's go with 3.
3? Okay, so 3. Given v, find x or a. And v is going to be the same function as I had before. So there's 2 ways I can go on this. Either go to acceleration or go to position. Let's go to position first because that's kind of beating the same dead horse we already just finished beating.
Yeah.
So I'm not going to write the steps now because it's the same steps. I'm going to replace now I want to separate the variables. And then I integrate both sides independently. And I have put in the limits. So there I put explicitly the upper limit and the lower limit on the right-hand side. And once again, this will simplify to I went rather quickly here because that is the same thing that we had for V. Exactly all the same work. So it's the same equation that we had right there. Or actually, that's not the one I wanted to circle. I wanted to circle this one. It's the exact same work getting to the exact same result, except for now it was X because I chose the same function. So that was quick because we've done something just like it. So now let's go the other way. If I want to find the acceleration, how do I find acceleration from speed? Okay, derivative of e to the minus bt, you bring down the derivative of the exponent, so you bring down a minus b. Derivative of ct is just c. A lot quicker doing the derivatives, right? A lot easier. That's why in calculus class you learn the derivative first. So that was both ways. Any questions about that option?
Can you make the acceleration one on the test?
Since the test is already printed, I can easily say, well, I'll think about it, and you know that I don't mean anything. I try not to give away what's on the test just because, you want people to be prepared for all of them. All right. Let's do one more.
You pick one of the last two.
Pick one of the last two, okay? Obviously, there's a lot of similarity between the two. I will randomly pick number 5. So V is B plus CX. This has B and X as variables, or excuse me, V is in Victor. V and X as variables. What substitution can I get to make it so I only have 2 variables and I have time as one of them?
Sorry, what were we trying to find?
We're going to try to find functions of time. We're going to try to find all 3 functions of time. Okay, V is dx dt. So I'm going to make the substitution. Okay, now what must I do? Following the same steps as we did before. Number 1, we had a substitution. Number 2 was separate variables. I need the x's on one side, the t's on the other, and I need the d's on top. Now, this is a little more complicated than what we had before. But I know 3 of the 4 of you are in Calculus 2, and I know you've done a lot of this in the last couple weeks. Well, 2 weeks ago you did a lot of this. So I need to divide everything by B plus CX. To get the x away from the right-hand side. And then I'm going to need to multiply everything by dt to get the dt over. And so what that gives me, I know my work here looks a little sloppy now, is dx over b plus cx is equal to dt. Okay, so we've separated variables successfully. Once you separate variables, it's always the same next step. And what's that? Integrate. Now, let me point out, I didn't have choices on how I was going to start this, whether I was looking for ultimately position as a function of time, speed as a function of time, or acceleration as a function of time. I had to do what I'm doing down through the next step first, simply so I could get a function of time. So when I do this, and I will tell you, I was chagrined to see that Nathan now does these quicker than I do. I have to do in my head a U substitution. And write the left-hand side as integral of du over c u Now, once I do that, now I can do it quickly. But I had to do that U substitution. I have to write it out. And so when I do the integral, I'm going to have... Now, I didn't write my limits, and I should have. So when I plug in my limits, that's the equation I get. Of course, I have to now substitute back in for u, and I will move the c over, so I will have that relationship. Well, I wanted to get this in terms of x, so I should go ahead and do my relax step. And use the inverse function of natural log. So doing both of those steps, I will have b plus cx over b plus cx initial equals e to the ct final. And so multiply everything across. And subtract b from both sides. And divide everything by c. I get my answer. There's x as a function of time. Now, if you look at this, this is not going to describe something realistic. It's not going to describe something realistic because as time gets larger, x very quickly approaches infinity, right? Because you have e to the positive ct. So that's something that's not very realistic. But that's okay. We're doing a problem here. We're not. So I didn't say, like with the car, we have the acceleration is proportional to this. It's not supposed to match reality here. It's going through the motions. So now we found position as a function of time. How do we find speed as a function of time? Notice we were given speed initially, but it wasn't a function of time.
Yeah.
Okay, so that's what we get doing it. Trace's suggestion. There's a second way we could get it just to make sure we didn't make a mistake. I had v is equal to b plus cx. My x function was this thing here. Whoops. Minus b over c. I could have substituted the x into that equation as well. It better give me the same result. Notice this c out front will cancel in each term. I'll have a b minus b, so those b's disappear. So b plus cx0 all times e to the ct. B plus cx0 all times e to the ct. They gave us the same answer, which is kind of important. If they didn't give us the same answer, we'd know there was a mistake. Self-consistency, good. And how would I find acceleration?
Acceleration is dv over dt.
Okay. Once again, we're all thinking like Trace. Boy, I hope he gives us one that has us using derivatives rather than integrals, because the derivative parts were much quicker than the integral parts. Any questions on the processes? We've done these before. We were just reviewing them today, and then you're going to be tested this afternoon on them. Any questions?
So it would be something like this, like just with letters, for example.
Well, you're going to have numbers to put in. I wouldn't put the numbers in until the end. I would do it all with symbols. Something that I was taught along the way is that a master problem solver feels more comfortable with symbols, right? We get to the point where the symbols have very strong meaning to us. Numbers can be confused. The symbols are obvious, right? If I have A in the middle of a formula, I know, hey, that A means the acceleration. Whereas if I have 2.35, I'm like, I don't know what 2.35 is. That could be anything. And so the master problem solver learns to see the symbols as meaningful and the numbers as not so meaningful, and tries to keep things in symbols as long as possible. Whereas the novice problem solver, when you were in first grade, numbers were really big, right? You learned to add, you didn't learn A plus B equals 5, you learned 2 plus 3 equals 5. And so the novice problem solver, they see the numbers as much more meaningful and the symbols as kind of esoteric. And so it's very understandable for students to like to put the numbers in early. And there's nothing wrong with that per se. Right? No one's going to mark you wrong for doing that. But over time, as you work more and more problems, you're likely to become more comfortable working with symbols as you start to get the feeling of symbols have meaning. So the bottom line is you put numbers in whenever you want. You're going to have numbers. You're going to have to put them in at some point. Any other questions? I should add, I'm not putting in numbers because, like I said, to me the numbers are rather trivial. The meaning is in the symbols. Okay, well then I will adjourn class if you have no more questions. Because that's my prerogative.